All right, welcome back. So today we are going to be going through some examples on how to graph and solve quadratic equations that are of the form ax squared plus c, and we're also going to be seeing them as ax squared minus c as well, okay? And let's just go to a diagram to show you what essentially happens with these functions. So when we talk about graphing these functions, f of x is equal to ax squared plus c, and again, we are also going to see end of ax squared minus c. There's two things that happen. So let me switch to my highlighter real quick. So if we are looking at f of x is equal to ax squared plus c, all this really is a shift vertically up c amount of units. So if we compare it to this blue graph over on your right-hand side, looking over here now, the blue graph is what's called the mother function. It's when c is going to be equal to 0. So that's just ax squared. When we look at the green graph above it, that's when it says that c is greater than 0. Well, it's the exact same graph as the blue graph, except it's just shifted vertically c amount of units. Okay. When we compare ax squared minus c, so let me go down here and write that ax squared minus c. Let me cross that one out for you. When we look at ax squared minus c, let me switch back to the highlighter. Okay, that is going to be the red graph underneath it. Notice how it says when c is less than 0, hence why we have the minus c value in there. All it is just a vertical shift down c amount of units. So we're comparing it to the quote-unquote mother function in the middle, the blue function. And the red graph is just the same exact graph except shifted c units down. The green is shifted c units up. When your c is positive, that means your y-intercept is going to be positive, it's going to be above 0. When c is negative, that means your y-intercept is going to be negative, which means it's going to be below 0. So that's why the vertical shift happens. There's one last thing that I want to draw your attention to. It's down here. It says the vertex of the graph of our general form f of x, you also see y, equal to ax squared plus c, is going to have the vertex of 0, comma c. And the axis of symmetry is going to be x is equal to 0. And that should make some sense, because if we want to find the axis of symmetry, well, that's x is equal to negative b over 2a, but we don't have a b value. So we would put 0. And 0 divided by anything is going to be 0. So we get that axis of symmetry being 0. So again, the vertex is going to be your y-intercept. Let me write that down for you. So the vertex is the y-intercept. Every single time we have this ax squared plus c or ax squared minus c, the y-intercept is going to be your vertex and is going to be along the y-axis. So let's show that. So if we want to graph this function here, x squared minus 2, the first thing that we want to do is graph our y-intercept, and we know it's going to be negative 2 because it's the constant term. So we have a couple ways of graphing, but I want to just introduce you to the table method. So again, we have our x and our y. We can just go to a simple input-output, and I'm going to start with 0 in the middle. I'm going to put 0 right here. Okay, when we have the input as 0, that means we're finding the y-intercept and we get negative 2. That's great. So I want to choose two values to the left of 0 and two values to the right of 0. So let's go negative 1, negative 2, then 1, and then 2. Now we only have to work with half of these values because a parabola is symmetrical. So if we choose negative 1 and we plug that in, right, we get negative 1 squared, which is 1. 1 minus 2 is negative 1. So we're going to have negative 1 right here. And also, it's going to, if we use 1, it's going to be negative 1 because it's symmetrical. Now we can use negative 2, plug it in. Negative 2 squared is going to be 4. 4 minus 2 is 2. and we can use it for 2 as well. So we get 2, 2, and 2, -2. We have 5 values. Boop. Boom. There you go. Notice that this does have roots to it. It does. It crosses over roughly here and roughly there. We haven't found the exact values of it, but it does have x-intercepts, and we can find them, and we're going to talk about that a little bit later, but I just want to talk about how to graph these functions first, and then we're going to talk about how to find the roots or to solve it. Great job. Let me go back to the pen. Smiley face, boop, boop. Nice. Cool. Here we go. So I want you to try these two on your own, and then we're going to come back and talk about them together. So, all right, if you listen to my voice, that means you have found the graphs for these two functions, and we are going to compare them. I'm going to graph the first function in blue and the second function in red, but I'm going to do it on the exact same graph. That way we can see the differences between it. So if I want to graph x squared minus 5, I'm going to graph my y-intercept first, 1, 2, 3, 4, 5. And then I can use my table. I'm going to use 0, 1, 2, -1, -2. Well, I know that when I have 0, it's -5. If I plug in 1, I get 1 minus 5 is -4, which means this is -4. If I plug in 2, I get 4 minus 5 is 1. -1, I should say. So I can now graph. I get 1, -4, and then 2, -1. So I can graph it. Woo! Woo! Sweet. And notice again, I do have x-intercepts. I just haven't found the exact values of them. But now if I go down to this second function, x squared plus 3, okay, I'm going to graph my y-intercept first, which is 3. And I'll make my table. Okay, I'll use 0, and I know I get 1, 2, -1, -2. When I have 0, my y value is 3. Okay, if I have 1, I plug it in. 1 squared is 1, plus 3 is 4. And then if I use 2, 2 squared is 4, plus 3 is 7. I don't know if it's going to fit, but we'll see something here. 1 and 4, -1 and 4. Let's see. 3, 4, 5, 6. Haha! It does fit. Look at that. Perfectly. So this is going to be the graph of h of x is equal to x squared plus 3. Notice this does not have any x-intercepts. It does not have any roots because it does not cross over that x-axis. And there is a reason for it, and I'm going to talk about that in just a second. But notice how they're pretty much the exact same graphs, just vertically shifted, right? There's a difference of, let's see, 1, 2, 3, 4, 5, 6, 7. There's a difference of 8 within all of these units. So if I count, I go 1, 2, 3, 4, 5, 6, 7, 8. That's 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All of these have a difference of 8. So they're the exact same coordinate. It's really the exact same graph. It's just shifted 8 units different. Okay? So that's how we talk about that vertical shift. The red is 8 units up from the blue. The blue is 8 units down from the red, and that can be determined from our C value. I have -5 and I have 3. Well, that's a difference of 8, right? Or difference of -8 depending on how you're looking at it. And that's how we talk about the vertical shift. So here is another core concept. When you have solutions of this x squared is equal to d, right? So if we're solving for it, so if I have x squared minus d is equal to 0, and then I get x squared is equal to d, that's how we get there. If this number d is greater than 0, it's going to have 2 real solutions by taking the square roots. If d is going to be equal to 0, it's going to have 1 solution where x is 0. And if this number d is less than 0, it's going to have no real solutions. okay? And the reason being is because we can't have a negative inside of a square root. So let's talk about why that is. So if I want to solve these equations, right? If I want to solve the equations using square roots, or I want to find the zeros of the function, let's talk about how we would do that. Well, for the first one, I want to get the x squared all by itself. So I divide by -3. X squared is equal to positive 25. And now to get x all by itself, I need to take the square root. When I take the square root, remember, I have a positive and a negative. It's going to be x is equal to positive and negative, 5. Come on. There we go. Right? For number 2, if I want to get the x squared by itself, I got to subtract 12. Right? We are going back to solving equations now. Now I have x squared is equal to -2. So I would get x is equal to plus or minus -2. But hold on a second, I have this negative here. I can't have a negative underneath a radical. So this is going to have no roots. Oh. For number 3, let's see what happens. If I want to get the x squared by itself, I got to add 15 first. So I get 4x squared is now equal to 0. Uh-oh. If I want to get that x squared by itself, I got to divide by 4. I get x squared is equal to 0. Now to get the x by itself, I have to take the square root. So I get x is equal to plus or minus 0, but it's really just 0. You feel me so far? Yeah? Cool? Sweet? Awesome. Now, what about these 3 down here? If we want to find the roots of these functions, how do we do it? Well, for number 4, I have x plus 7, that quantity squared is equal to 0. I can take the square root, both sides. So now I get x plus 7 is equal to plus or minus 0, but it's really just 0. So I get that x is going to be equal to -7. That means it's going to be passing through that x-axis only at -7. For 5, what do we have to do here? Well, I have 4 times a quantity, x minus 3 squared is equal to 9. Well, I need to divide by 4 first. So I get x minus 3 squared is equal to 9 over 4. And now to get that x minus 3 all by itself, I have to take a square root. So I get x minus 3 is equal to plus or minus now. Well, the square root of 9 is 3. The square root of 4 is 2. So I get this final answer of x is equal to 3 plus or minus 3 over 2. That happened because I added 3 to both sides. Likewise, for number 6, I have 2x plus 1 squared is equal to 36. I can just take the square root of both sides here. So I get 2x plus 1 is equal to plus or minus 6, as a square root of 36 is 6. I want to subtract 1 on both sides. So I'm going to get 2x is equal to -1 plus or minus 6. And lastly, we want to get that x all by itself, so we got to divide it all by 2. So we get x is equal to -1 plus or minus 6 all over 2. Awesome job so far, folks. Awesome, awesome job. Okay? So we are going to actually stop here, and then tomorrow we are going to pick up again on this key concept of what's called rationalizing the denominator. Notice how all of these square roots came out to be easy numbers for us to operate, and sometimes it doesn't happen, right? But the reason that we want to solve these equations by square roots is because we want to see how many roots that function has, how many times it passes through the x-axis. So, for example, if we go back to the first one we did, x squared minus 2, well, then we get x squared is equal to 2. That means x is equal to plus or minus root 2, and that's going to be these x-intercepts. Great job, everyone. If you have questions, reach out via email.